up, guys? I think it's day 6, maybe day 6 of programming every day until I get a job. We're gonna look at some more Leetcode here, and probably do the question of the day too. Looks like I actually have the roadmap open right here. We were looking at some trees a couple days ago, but I kind of want to finish some sliding windows. I think we did this one yesterday, but maybe we want to do permutation in a string, maybe we can do that one, and then we can complete our question of the day, and then I don't know, maybe we can do like a tree problem or something. I don't really. Maybe we can attempt a hard problem too. I don't know. I've only ever really completed one hard problem that was with a lot of extra help. So I don't know. We'll see. I guess we'll start with this one: permutation in a string. Let's take a look. Permutation in a string. Okay, given two strings, S1 and S2, return true if S2 contains a permutation of S1 or false otherwise. Otherwise, return true if one of S1's permutations is in the substring of S2. So they say this is a sliding window problem. They have a lot of hints for this one. I was thinking a hash table, a dictionary. I don't understand how a sliding window would come into play here, because can't we just store what we want to find? Store S1 in our hash map. And then just like loop over string 2 and just see if it's in the hash map. And if it is, we return true. Like, I'm going to try and complete it with a sliding window. I think you can just do it normally. Is there a permutation in this? I think we're going to start off by just sorting here. I just want to make sure this is how you do it. Is it sorted or is it sort? I can never remember, man. Like, just say a string in Python. God, man, I can never remember. Like, there's no attribute sorted. Sorted S1. Sorted S2. Okay. Alright. So we sorted them. trying to think what we can do. Trying to think how we can use a sliding window here. Oh wow, that's cool. I think they just added this. 112 online studying this problem. I'm thinking, what the fuck is this? Oh, it's a time of accident. Trying to figure out how we can use a sliding window to make this happen. This is one we did yesterday. Right, and I think it was this one too. It seemed like the longest upstream. God, I picked the same one. Trying to think here. So now that we have it sorted, we can kind of loop through. I'm thinking we put this in a hash map. Right. Then we loop through. We have the size of the string, right? So we know how big our window needs to be. And we just keep looping through. And if they're all there inside the hash map, then we just return true. I don't know if that's crazy, but that's kind of the way I'm thinking about it right now. So I guess we can do length here is length of S1. For in S1, we want to create a dictionary. Create a dictionary. For char in S1, if char is in length or dict, then we want to S1 char is equal to plus equal 1, right? Else S1 char is equal 1. I don't know if that's the proper way of doing it. That's right. Maybe we want to do a range in chars in my dict. I think we want to do minus. Need that. Right, I think so. Let's run that and see if that works without any errors. Chars in my dict. Well, I think we have to do if. All right. Yeah. I don't know if this only applies to an array, because here we were looking at an array. I think it might. Invalid syntax. If S1 char. What we're gonna need is there is no is. Whoops. Oh shit! I'm gonna sneeze. Okay, nice. Put our values in. All right. So now we want to create our left. Our left is equal to 0, right? So we did over here. We had our left. Right in range S length S2. We want to check how do we make the window size I guess we want to start from like start from length, right? Would you want to start from the length of the S1? I guess we can do a little while loop here while left is less than right. I think here. Guess this is our window length, right? No, we don't want to start from there. We want to go through everything, but I don't know how to do this in code. I generally don't. Try and visualize what I'm trying to do. So we have. Can I type in here, bro? Can I make like a text box or something? Man, I hate drawing with the mouse. Pretty much here we got our string AB, right? And this is installed. This is inside of our dictionary, right? See if I can draw this. This is inside of our dict. Then we're looping over S2, right? Loop S2. And we're trying to check. By the way, these are sorted, right? S1 and S2 are sorted up here. So they're sorted. Which means we'll run into them, right? So we loop over S2 and we just This is the worst S2 ever. This is meant to be a 2, by the way, and this is meant to be an S. So we loop over S2, and we're just checking to see if A is in there and if B is, and then we decrement, right? By 1, if we see it. Right? And then we remove the value, right? And I guess if our dict is empty, then we return true, because there is a permutation there. So that's kind of the way that I'm thinking about this, but I just don't know how to implement this last little bit with the sliding window. And obviously, like with the sliding window, we're only checking the size of this, and we're moving the window each time. So we check the first 2 values, this one, and this one, and then we move, we check 2, 3, right? And we have like 4 here, and this is the array, so we're just checking the window, but we're moving the window as we go, but I'm not sure kind of how to begin. We initialize our left is equal to 0, and then we no. So yeah, this is tough. I'm gonna ask ChatGPT. I'm gonna ask him how we can do this last for loop down here. For loop, pretty much. I'm trying to loop through string S2 with a sliding window with window underscore length is equal to an S1. Checking to see if each value in the window is present in the dictionary. If it is, we return true because we found permutation. Okay, let's see what they do here. So, initialize dictionaries to store frequencies. So they have the window length, they have the original dictionary that I had, and they have a window dictionary. Okay, wait. Oh, they're checking to see if that's a smart way to do it. I never thought about that. So what we're going to do is we're going to create a window dictionary here. And pretty much what we're going to do is we're going to compare everything. So we're going to compare. So for right and length S2, add current character to the window dictionary. Where's that current char? Where do we initialize that? Okay. Alright, so we create a current char. You make that equal to S2, right? Then we want to add it to our dictionary. And underscore current char. Oops, current underscore char is equal to window dot underscore dig socket current underscore char 0 plus 1. So I assume that it gets the current char. If it's already there, it assigns. If it's not there, it assigns 0. And if it is there, then it increments the current char by 1. I think that's what this is probably doing. Right? If right is greater than or equal to window length. Okay. So if right is greater than or equal to window underscore length. So if right goes past the window length, when it reaches window length, we remove a character at the left end of the window. If left underscore char is equal to S2 sorry, not yet. What am I doing? You have to make a pointer for the left. Left char is equal to window length minus right. I guess technically right could be greater than. So I guess you should put that first. Which I don't think it can be. Window length. Okay. If window left char is equal to 1, else okay. So here now we're checking in the hash map. Left underscore char is equal to 1. Then we want to just remove it. Okay, that's what they have here. I didn't know that it was like a straight delete. I didn't know that. We can delete. Window underscore dig, left underscore char. Else, if our window underscore dig, left underscore char is greater than 1, then oh no, we don't need to do another if. We can just do left char minus or equal to 1. Right? Yeah. Yep. And now finally, we need to check if minus is equal to window underscore dig, and we can return true. right? Yeah. Otherwise, we return false. Nice. It's easy to me to kind of like sometimes. Sorry, I'm getting so many texts. It's kind of easier for me to kind of like think about the problem in a way. And kind of, I understand kind of how to approach it because I have that material, but it's hard for me to put that into code. That's what I really struggle with, especially with like Python code and stuff like that. Because it's been a long time since I've worked with Python. I'm not too sure about the syntax, and that's something that I really got to improve at. So, but I feel like that comes with the more problems that I do. The better I'll be at kind of one, obviously I'll be better at approaching problems, and two, should be better at the syntax. Let's just see if this submits, hopefully. Nice. Oh, look, it was the most optimal way of doing it. That's interesting. But I think, we could approach this, a different way. I don't know. I think you could easily brute force this too. But I don't know. Let's see what the slowest possible way was. See what they did. So it looks like he's splitting window is equal to S2 length S1 minus 1 for I in range length S1 minus 1. Like that's to window plus or equal to S2I. If S2I in S1 and window I guess this one trying to think. I'm not really 100% sure what this does, to be honest. What does this line do? I don't think this is brute force. No, it is a brute force approach. This code is brute force approach. You should break down why it's considered brute force and how it works. Initial window setup. This line initializes the window with the first length S minus 1 characters of S2. Loop iterates from index. Character S2I. See, I'm a little still kind of confused. Maybe like of S2 is a permutation of S1. Take the first length S1 minus 1. No match. Remove the first character to keep the window size constant. Oh, okay, right. Then we add the next one. No match. EVA, we have a match. Oh, that's a smarter way of doing it. I mean, mine's faster, but that's a smart way of doing it. I didn't really think about that. It's interesting. Hmm. This is what we did. Interesting. All right. Well, let's head to our next bubble. Let's do the question of the day. Oh man. Ah, my back. Oh jeez. So I think we did this one yesterday, actually. Yeah. This one was just crazy, man. Okay. Geez, it's gonna be mediums forever. Oh, we got some hards. Oh god. Not bits. I fucking hate bits. Okay. Some square numbers. Get a non-negative integer c. Decide whether those two integers a and b such that a squared plus b squared is equal to c. Okay, well, we got a is equal to 0. B is equal to the square root of C. Right? Is equal to C. Obviously, want to make this actually an integer too. It needs to be a whole number. B squared is equal to B plus C. B squared is equal to C squared. And we can oh shit. And return true. Else if we need a while loop. Oh, A is less than B, right? Because it can't be any bigger. Else if if ans is greater than c, then maybe we want to decrement b, else a plus equal to a is equal to 1. We can just return false. Maybe we swap it around if ans is less than c, and we increment a, else. I don't think it's going to change at all, but I'm just curious. Oh shit, I fucked that. Yeah. Didn't really matter at all. I'm trying to. Well, let's go through this. 0. Okay, let's pull up paint here. Okay. We have a is equal to 0. V is equal to square root of 5. Which is 2. Right? While we enter the while loop, while a is less than b, I'm going to check 0 squared is 0 plus 2 squared is 4. So we have our answer is 4. We go on to this. If is 4 equal to c? No, it's not. If 4 is less than c, a plus c equal to 1. So then our next loop will be a is equal to 1, b is equal to 2. 1 squared is 1. 2 squared is 4. Which is 5. And 5 is equal to 5, return true. the fuck is this messing it up? Like, well, A is less than B. Is my math off, dude? Like, what? Okay, yeah, that's 2. Is this how you fucking... Maybe I'm adding this wrong, dude. No way. C is equal to 2. Okay. Oh. Okay, if A is equal to 0, and we have B is equal to square root of 2, which is 1, right? So then we have A is less than B, yes, A times A is 0 plus 1, so we should return 1 here. Let's use this as a test case and run it. Yep, so we get 1. We get 1, right? So then that ups A, so then we have 1, 1. Okay. A is equal to 1, B is equal to 1. 1 squared is 1, is 2. While A is less than B. Oh. Has to be equal. There we go, baby. Well, obviously that was a way easier solution. All divisor times divisor is less than or equal to 0. What? Well, divisor times divisor is less than or equal to 0. See, my solution seems way easier. Like, got some like Chinese or something here. Interesting problem. Interesting problem. I just like looking at random people's profiles. 202 problems solved. Damn, bro. Someone in TypeScript. Damn, bro. Okay, let's continue. Let's try and fit in one more problem. Let's do trees. We like trees. Let's check out bounce. Not very good with trees. Oh, have I already done it? I don't know if that means if I already done it or not. Nope. Okay. In a binary tree, determine if it is height balanced. What does that mean? If root is non-true. Let's see if I get that. Yeah, baby. Yeah. Okay, I don't know what. Given a binary tree, determine if it is height balanced. A height balanced binary tree is a binary tree in which the depth of two subtrees of every node never differs by more than one. I still don't really know what that means. There must be some like pattern or something, I think, to determine if it's height balanced. Because I have no idea what the pattern is. I was thinking before that it was like a distance of 1. Every node differs by more than 1. This is more than 1, this would be false. Looks like it's true. I have to give myself a little bit of a refresh again with BFS and DFS. I remember watching
Today,
this when I
I'm
was
going to
in my
teach you
college
breadth
classes.
first search. Breadth rests horizontally. For keeping track of vertices is a queue, top, width, and edges. A. Nodes we find to be visited will be colored gray. Starting our algorithm, A is the first node we'll visit. We'll keep track of the queue in the top left corner. We pop A from the queue and mark it as visited. We also add its adjacent nodes into the queue. B is the next node out of the queue. Same with C. We visit D is the next item out of the queue. There's a link to a working Python example in the description. The code is very similar. Today, I'm going to teach you depth first search. We want to away stack. We also rightmost node first because I think it's easier to follow. We also add its adjacent nodes into the stack. I'm adding the rightmost node first because I think it's easier to follow visually if we go left to right. B is the next node popped from the stack. We mark it as visited. Nodes. G gets moved to the bottom. C and D have no children, so nothing to add to the stack.
To be honest, I'm not sure how to solve this problem. Let's do reverse balanced. Okay, the depth of two subtrees of every node. More than one. So if we do DFS, we go 1, 2, 2. I think this is why it's false, because the depth here is more than 2. But here it's good because 3, 9, 20, 3, 9, 20. But how do we know that it's... I think I understand why, because it's like, if it's height balanced, the depth of two subtrees, every node differs more than by one. This one differs by more than one, so it's unbalanced. This one doesn't, because we've got one level here. But I'm not sure kind of how to calculate that. That's the thing.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem balanced binary tree. We're given a binary tree and we want to determine if it is height balanced. What exactly do they mean by height balanced? Well, it's defined by saying that for every single node in the tree, if we take the left and right subtrees of this node, the heights of these left and right subtrees will differ by at most 1. So in here you can see, taking a look at the root node, it has a left subtree. What's the height of this left subtree? Let's call it 1, right? Because there's one node in the left subtree. What about the right subtree? What's the height of this right subtree? Well, it's 2, right? We can determine that just by looking at it. So then the left subtree has a height of 1, the right subtree has a height of 2. The difference is at most 1, right? Because if we take the absolute value of the difference, we get 1. So we'll say the difference is 1. So we just did that for the root node, but we have to do that for every single node to make sure that the left and right subtrees of every single node differ by at most 1. And just to show you a counter example, so this is kind of a badly drawn tree, but take a look at the root node, right? If we take a look at the left tree over here, the height is 3. If we take a look at the right subtree, the height is 3. So the difference is 0, which fits into our criteria. So from the root node, the left subtree and the right subtree are balanced. But if we take a look at, let's say, this node, right, we take a look at its left subtree, which is empty, right? So that has a height of 0. The right subtree has a height of 2. So in that case, the difference is 2 minus 0, which is 2, right? Positive 2, which is greater than 1. So just because from here, taking a look at the root node, the left and right subtrees are balanced, doesn't mean that that's going to be true for every single node, because we just looked at this node, the left and right subtrees were not balanced. How can we solve this efficiently? Let me first show you kind of a naive approach, and then we'll see how we can actually optimize that. So if we were asking naively, right, the first question we're asking is, from the root node, are the left and right subtrees balanced? How do we even determine that? Well, do you agree that we could probably do a recursive DFS on the left subtree to determine the height of the left subtree, do a recursive DFS on the right subtree to determine the height of this subtree, and then we could compare those and make sure that the difference is less than or equal to 1. Do you agree that we could do that? Probably, right? I'll explain more details in the code, but for now, let's just assume we can do that. We start from the root, we run a DFS on the left and on the right. That means we go through every single node in the tree, so we just did an O of n operation, right? And we were able to determine, okay, from the root node, yes, it is balanced, but we're not done yet, right? Now we have to continue to ask that question for every single node, right? So the next question we're going to ask is, suppose on the left subtree, right? From the left subtree, are the left and right subtrees from this node also balanced? And of course, they're both 0, so we determine that they are. And then we'll have to recursively go to the right subtree. From here, we're going to ask, are the left and right subtrees balanced? Yes, they are. but we'll recursively have to continue. We'll have to do that from this node, and then we'll have to do that from this node. Since we're running a recursive DFS on every single subtree on this root tree, we're going to have to do basically an O of n operation each time we ask that question. Is it balanced from here? Is it balanced from here? Is it balanced from here? And we can have a really big tree, and we'd have to do an O of n operation each time. O of n is the number of nodes in the tree, and if we have to do this n operation n times, we're going to get a time complexity of O of n squared. So now the question is, can we do better than that? Is there any repeated work? And I'll show you that yes, there is repeated work, and it basically can be eliminated by asking the question in a different order. What I mean by that is, instead of first asking if the entire tree is balanced from the root node, right? That's the first question we ask. Is it balanced starting from here? Instead of asking that, we do this bottom up. We recursively, instead of asking it from here, we're going to check, okay, is this entire right subtree balanced? Before we do that, we're going to ask, is this entire subtree balanced? And we're going to keep going lower and lower until we get to the base case. Once we get to the base case, then we're going to go back up, and I'll show you how that's actually going to end up eliminating the repeated work. If we do it in this order, we'll only have to visit each node at most one time, which will ensure the overall time complexity is going to be big O of n rather than n squared. Okay, so when we get to the root, before we check if it's balanced from here, we're going to check if it's balanced from this right subtree. That makes sense so far. And then before we ask from this position, we're going to ask, is it balanced from this leaf node, right? And now we can't really go any lower because this node doesn't actually have any children, so of course its subtrees are going to be balanced. But now we're good, right? We determine, okay, from this node, yes, the left and right subtrees are balanced, right? And then we pop back up, suppose, and then we also want to make sure that this node is also balanced. It's the same thing, right? The left and right childs don't exist, so yeah, it's balanced from here as well. So we determined that, right? Now we know from at least these two nodes, yes, the left and right subtrees are balanced from these two nodes. Okay, now we want to know, is it balanced from this node? How can we determine that? Aren't we going to have to go back down and revisit the entire right subtree and the entire left subtree again? No, and I'll show you why. As we are determining if this subtree is balanced, let's also at the same time, simultaneously, let's make sure we get the height of this tree, the entire height of this subtree, and let's do the exact same thing for this node. Make sure we get the entire height of this subtree, because once we've done that, then once we go back up to the parent node from here, it will be easy. We already have the height of this tree. We already have the height of this tree. We can take the difference between those, make sure it's less than or equal to 1, and then we're good. We didn't even have to revisit these trees, right? From this node, now we've already determined, yes, it's also balanced from this position, right? So now we've determined it's balanced from this node, balanced from here, and balanced from here. And now we want to go back up to the root node and make sure it's balanced from here. Before we do that, we have to solve the subproblem on this left subtree. It's just a base case problem, right? It's just a single node, so we know it's balanced from here as well. So now we want to go back up to the root node. Is it balanced from this root node? Well, as we are doing this, right, as we were doing this right subtree, we determined that the height of this tree was 1, the height of this tree was also 1, right? So now we want to know, before from this node over here, before we return back up to the parent, we want to know what's the entire height of this subtree. How can we easily determine that? Well, we know that this was 1, this was also 1, so from here the height is just going to be 1, meaning this 1 comes from this node over here, plus the max of its left and right subtrees, which we know are both 1, so we can take the max of 1 and 1. That's going to end up being 1, so the height of the overall tree is just going to be 1 plus 1, which is 2, right? So the height of this tree is going to be 2. We determined that pretty easily, and that's what we can return back up to this parent node, which is good for us, right? And from this tree on the left, the height is 1 because it's just a single node, so we return that up to the parent as well. So now from here, we know that the height of the left subtree is 1, the height of the right subtree is 2. We can take that difference, 2 minus 1, it's 1, which is less than or equal to 1, so that we do know that this is balanced from this node as well, right? And we can continue to recursively do that. If we had another parent node up above us somewhere, we could return, okay, the height of this overall tree is going to be 3, right? So that's the main logic we're going to follow. Yes, we're going to do this recursively, and there's many ways to code this up. The main way I'm going to code this up is actually by returning two values. I'm going to return a Boolean as the first value, which will be either true or false. Basically, for every single subtree, remember, we are going to determine is that subtree balanced. We'll return a true or false for that. And the second value will be the height of. Okay, so now let's get into the code, and the main thing is we're going to do this recursively. Why can't I just use this outer function to do it? Because this outer, we're going to pass in a single parameter, which is the root, and remember this function is going to return a pair of values, a Boolean and the height of the tree. So first things first, the base case. If the root is null, right, this means that we have an empty tree. So is an empty tree considered balanced? Yeah, let's say it is. So for the first value, we'll return true in this case. And the second value, which is the height of the tree, an empty tree we can assume just has a height of 0, let's say. And now, remember, before we determine from this root node, is this tree balanced? First, we want to determine if from the left subtree it is balanced, and from the right subtree is it balanced. So let's call DFS recursively on the right and left subtrees, and then assign it to the result variables left and right. So that's what we're doing with this single line of code, calling DFS on both subtrees. So now we want to know from the root node, is it balanced, right? How can we determine that? Well, we're going to have to take the absolute value of the left and right heights, right? So how can we do that? We can take absolute value left of index 1, because remember the second value is where the height happens to be, left of 1 minus right of 1. So this will give us that. So as long as this is less than or equal to 1, we can say that the tree is balanced, right? Not so fast, because remember, if either of these left or right subtrees ever return false in the first parameter, then we know for sure that the entire tree is not balanced, right? So before we say that this condition is enough, we're going to add two more conditions. We're going to say, okay, as long as this is true, meaning that from the root it's balanced, and the left and right subtrees were also balanced. So we can determine that by just taking the the 0 index of left and the 0 index of right, and also this condition over here. Let me just reformat it slightly to make it a little bit more readable. This balance is what we're going to be returning as the first, as the 0th index. Let me just show you that. So we're going to return a pair of values. The first is going to be, is this tree balance, and the second is going to be the height of the tree. How do we determine the height of the tree? Well, it's going to be 1. 1 comes from the root node that we're currently at, plus the max of the left and right subtree, so we can get that pretty easily. Left at index 1 and right at index 1, so whatever the max of those two is, plus 1 gives us the height. Hopefully this is pretty simple, but the balanced might not be. This balanced doesn't only mean is the tree balanced from the root position. This balanced means is the entire tree balanced at all. Because remember, if the left subtree, for example, was not balanced, then this conditional is going to evaluate to false, right? Because this balance is only going to be true if the left subtree was balanced and the right subtree was balanced, and from the root subtree are we balanced, right? So all three of those have to be true for us to return true as the balanced variable. Hopefully that makes sense, because that is the entire code. Once we're done with that, we can, in the outer function, we can go ahead and call our DFS starting from the root node. And remember, this DFS is going to return two variable, or a pair of values, right? A Boolean and the height. So which of those do we want to return in the outer function? We want to return the Boolean, so we can return this at index 0, and then that'll be the entire code.
These tree problems are tough, man. Left DFS root. If not root. Right, okay. So then we want to check the left. DFS, and then the root we want to check is left dot root. Right? Root dot left. Okay. Jeez. Root dot left. Alright. Alright, let's switch to DFS. Root dot right. Okay. If the absolute value of left minus right greater than 1, you return false. Oh, whoops. Self-balanced is equal to false. Self-balanced is equal to true. And the max left, right, plus have a root. Or DFS root. You want to return top balance. I just don't really understand these problems properly. Like, I don't really understand how to I'm really gonna have to look back at some of these data structures like trees and stuff because I really cannot remember left is equal to DFS. Huh? I'm gonna call it for a day though. It's been a while. Gives me kind of a headache doing these problems, to be honest. Yeah, we'll keep looking. So yeah, we'll keep going. We'll get better. This really just takes doing the problems over and over again, just seeing them again and understanding better and so forth. So I'll see you guys later. See you guys tomorrow.